Alright, as promised, I said I would go through these stoichiometry problems so that we understand what we're doing for the test, which will come next week. So, first one, is the equation balanced? We can pretty much safely assume these are balanced, but I do have two sodiums, two sulfurs, two sulfurs. In this particular situation, I have 3 plus 5 oxygens. That gives me 8 oxygens, which 2 times 4, I have 8 oxygens here. 8 chlorides, 10 hydrogens, that's 2 hydrogens, that's another 8, that's 10 hydrogens. Everything's balanced. So, is the chemical equation balanced? Yes. What are the mole ratios? It would be 1 sodium thiosulfate to 4 chlorine gas to 5 waters to 2 sodium hydrogen sulfates to 8 hydrogen chlorides. I just want to check and make sure that's legible. It is. Okay, so what does this mean? It means for every 1 mole of sodium thiosulfate, which again, you don't have to worry about the name of that ion, but what you need to know is for 1 mole of this stuff, I would need 4 moles of chlorine, I would need 5 moles of water, and if I have those requirements, I would make 2 moles of sodium hydrogen sulfate and 8 moles of HCl, which is hydrogen chloride, although when hydrogen chloride is dissolved in water, it is hydrochloric acid. Now, how many moles of sodium thiosulfate are needed to react with 0.12 moles of chlorine gas? So what I always do is I write down, to anchor myself, what I am given. I'm given that. I have 0.12 moles of chlorine. What am I asking for? How many moles of sodium thiosulfate? So, using my mole ratio, I'm going to figure out how many moles of sodium thiosulfate I would produce. So, what I want on the top, 1 mole of sodium thiosulfate. Now, what does this ratio mean? If I have 1 mole of this, I need 4 moles of this. If I have 4 moles of this, I need 1 mole of that. That's what I'm trying to set up here, right? If I have 4 moles of chlorine, I need 1 mole of sodium thiosulfate. If I had 8 moles of chlorine, I would need 2 moles of sodium thiosulfate. So the ratio is always, no matter the quantity, 1 to 4, as I see each time. What I want is, now I've set up a conversion, so I will turn my moles of chlorine gas into moles of sodium thiosulfate. So 0.12 divided by 4 is 0.03 moles of sodium thiosulfate. That is the answer for that. How many moles of sodium thiosulfate are needed to react with 0.12 moles of chlorine gas? That is how many. How many moles of hydrogen chloride or hydrochloric acid can form from 0.12 moles of chlorine? So we again have 0.12 moles of chlorine, but this time I want to look at HCl. So I'm going to do my conversion same way based on this mole ratio. 8 moles of HCl, which I pulled from my equation, and that tells me for 4 moles of chlorine gas, I would make 8 moles of hydrochloric acid. So I'd get my ratio again. It's the same exact ratio I have each time. Moles of chlorine cancel out. I'm left with moles of hydrochloric acid. In this case, it is 0.12 times 8, which would be 0.96. 0.96 divided by 4. If I had my calculator, it'd be a lot easier. So, 0.12 times 8 equals 0.96 divided by 4 equals 0.24 moles of hydrogen chloride or hydrochloric acid, because my mole ratio is 8 to 4, which is basically the same thing as for every mole quantity of chlorine I have, I make double my hydrogen chloride. So basically I'm doubling the hydrochloric acid. That is what this relationship means. And that is why I need to go through a mole ratio each time to make this happen. Alright, now I need to move my paper up a bit. Give me a chance to line it up. Not quite. Okay, try this again. A little crooked. Let me get it lined up first, then I'll tape it down. Alright, almost there. So now we have how many moles of water are required for the reaction of 0.12 moles of chlorine. So in this case again, same thing we've been doing. 0.12 moles of chlorine. Now my mole ratio, if you remember, you can't see it at the top of the paper, I don't think, but you can see it at the top of your paper. So that would be, what do I want? I want my water, and I want my chlorine again. These are going to cancel out, my moles of chlorine. So this would be 0.12 times 5, which is 0.60. If you don't believe me, 0.12 times 5 equals 0.60. Divided by 4 is 0.15 moles of water. That's the only thing that did not cancel out. And then the last one, if I'm forming, and again I write down what I'm given to anchor myself, 0.24 moles of hydrogen chloride, going to feed that through the mole ratio. It's asking for water. So my original mole ratio, 5 moles of water to 8 moles of HCl, because that is what my equation said. And in this case I get 0.24 times 5 equals 1.2 divided by 8 equals 0.15 moles of water, because I canceled out my moles of hydrochloric acid. As long as things cancel out, I know I did things correctly. Alright, so our first page is done. Moving on to the second. We have another equation. It's asking if it's balanced. Now, I'm going to give you, on your test, balanced equations, but we should just double check, just to be safe. Get it a little bit better lined up. Okay. So, what do I have here? Na2, 2 sodiums, 2 Nas, 2 sodiums, 2 oxygens, and that would be 6 oxygens. Here I have 6 oxygens. Here I have 2 hydrogens, 4 hydrogens, 4 hydrogens. Everything is balanced. So is the equation balanced? Yes. What are the mole ratios? Now again, in my step-by-step procedure for stoichiometry, balanced equation, units to moles, mole ratio. Could you do the mole ratio ahead of doing your conversions? Absolutely. But the mole ratios are 2 moles of NaOH, which is sodium hydroxide, to 1 mole of sulfuric acid, to 2 moles of water, to 1 mole of sodium sulfate. How many moles of water will be produced when 0.58 moles of sulfuric acid is consumed? Again, we don't have to do unit conversions in these particular cases because we're working with moles. Although when we get to the next one, we actually will start having to deal with unit conversions. So, how many moles of water will be produced when, this is my thing that I'm given, 0.578 moles of sulfuric acid. Now it's saying how many moles will be produced when that much reacts. What's the relationship? 2 moles of water for 1 mole of sulfuric acid. Now if you're really good at math, you could just double that number when you realize that. However, if I set this up in the proper relationship, I'm going to make my life a lot easier. So 2 moles of H2O. I pulled that from my mole ratio up here, or over here, and 1 mole of H2SO4 sulfuric acid, because it's a 1 to 2 relationship. My moles of sulfuric acid cancel out. I end up getting 0.578 times 2, which is 1.156. Now, if I were really worried about significant digits, I really can't have 4 significant digits. I'm going to need less, so I would need 1.16 moles of what's my thing that's left over? Water. Okay. How many grams of sodium sulfate will be formed if we start with 200 grams of sodium hydroxide and you have an excess of sulfuric acid? The excess means we are not going to run out of sulfuric acid. We will run out of sodium hydroxide. So in this particular case, my process, 200 grams of sodium hydroxide. I have units here. Now I'm going to go units to moles. This is what we've done before. I'm going to use grams because I need to go from grams to moles. Because I'm given grams, I need to divide this by the gram molar mass. For sodium hydroxide, how did I do that? Sodium's 23, which I could see on my periodic table. Sodium is 23 plus oxygen, that's 16. 23 plus 16 is 39 plus 1 hydrogen is 40. So 200 divided by 40 is 5 moles of sodium hydroxide. Now it's asking how many grams of sodium sulfate. I can't do that yet. I have to put this through my mole conversion. So 5 moles of sodium hydroxide, the same thing we've been doing. Now I have to take moles of sodium hydroxide, turn them into moles of sodium sulfate. How do I do that? 1 mole of sodium sulfate over 2 moles of sodium hydroxide, which I pulled from my original equation. My moles of sodium hydroxide are going to cancel out. I get 2.5 moles of sodium sulfate. That's still not my answer though, because it says how many grams. So now I need to go from moles to grams. So first I need to figure out what my gram molar mass for sodium sulfate is. Na2. So it's 23 23 times 2, which is 46, plus sulfur, which is 32, plus 4 times 16, which is 64. My gram molar mass for sodium sulfate is 142 grams over 1 mole. And again, I've lined this up so my moles will cancel out. So I get it's basically 2.5 times 142, which is 355 grams of sodium sulfate. That is my answer. Is that what the question was asking for? This is why I love stoichiometry. You've got to ask yourself these questions. How many grams of sodium sulfate? Do I have grams of sodium sulfate? Absolutely. I'm done my problem. I start with 200 grams of sodium hydroxide. I make 355 grams of sodium sulfate. This is a beautiful stoichiometry problem. We'll see another one on number 3. Let me see if I can slide it up properly. Slide it up a little bit more. So in this particular case, let me just slide it a teensy bit. Okay. So now I have lead 4 sulfate, lithium nitrate, lead 4 nitrate, lithium sulfate. If you really know your stuff, this is a double replacement reaction. Is this chemical reaction, so is this chemical equation balanced? 1 lead, 1 lead. 4 lithiums, 4 lithiums. 2 sulfates, 2 sulfates. 4 nitrates, 4 nitrates. I'm balanced, so yes. What are the mole ratios? 1 mole of lead sulfate, lead 4 sulfate, to 4 moles of lithium nitrate, to 1 mole of lead 4 nitrate, to 2 moles of lithium sulfate. Where did I get that mole ratio? I got it from my balanced equation. How many moles of lead 2 sulfate are needed to produce 2.35 moles of lithium sulfate? So I anchor myself by writing down what I know. 2.35 moles of lithium sulfate. So how many moles of how many moles of lead 2 sulfate? And you know what? This is actually written wrong. This should be lead 4 sulfate. There's a need for a correction. But anyway, how many moles of lead 4 sulfate? This is the danger when you get things off the internet. How many moles of lead 4 sulfate are needed to produce 2.35 moles of lithium sulfate? I have my moles of lithium sulfate. I need to find my moles of lead 2 sulfate. So how do I do that? Put my mole ratio in here. 2 moles of lithium sulfate. Moles are going to cancel out. Moles of lithium sulfate are going to cancel out. And then what goes on top? Lead 4 sulfate. 1 mole of lead 4 sulfate. So 2.35 times 1 is 2.35 divided by 2 . 1.175. Again, we're dealing with 3 digits, 3 sig figs. So it should be 1.18 moles of lead 4 sulfate. That is my first thing. That only asks for moles. However, the second part is again going to ask for grams. How many grams of lithium nitrate would we need to make 250 grams of lithium sulfate? Assuming you have an adequate amount of lead 4 sulfate to do the reaction. So we're going to have excess. We're going to have more lead 2,4 sulfate than we need. We're going to have more lead 4 sulfate than we need. We're going to run out of lithium nitrate when we're trying to make lithium sulfate. So what do I know? I know I have 250 grams of lithium sulfate. I can't just go ahead and do my canceling out because we only do canceling with moles, not with grams. So the first thing I need to do is turn this number into moles. I have to convert units. So I have a balanced equation and then I convert units. So lithium, I have 2 lithiums. Lithium is 6.9, we'll say, times 2 is 13.8. Then I have a sulfur, which is 32. And then I have 4 oxygens, which is 64. 109.8 is the gram molar mass. So it's going to be 1 mole over 109.8 grams. My grams cancel out. And I get 250 divided by 109.8, which is 2.28 since I'm dealing with 3 digits. Really, there's only 2 significant digits here. This should be 2.3. I mean, if we really want to get technical with our sig figs. 2.3 moles of lithium sulfate is what I have. However, that is not what my question is asking. I'm going to move this up a tiny bit to make sure I have enough room. Alright, from there, I know how many moles of lithium sulfide I have. Now I can convert lithium sulfate into I can now convert lithium sulfate into lithium nitrate. So I'm going to go 2.3 moles of lithium sulfate. That was our original product. I'm going to do my mole conversion now. What is my mole conversion? I want lithium nitrate on the top. 4 moles of it. I got that from my original equation. And then I have 2 moles of lithium sulfate in my original mole ratio. That way, these moles cancel out. 2.3 times 4, that is 9.2, and then I have to divide that by 2. 4.6. My only units remaining are lithium nitrate, which is what I wanted to find. So I have 4.6 moles of lithium nitrate. Now from there, the question is how many grams? I have moles. Gotta go from moles to grams. So I have 1 mole at the bottom. That way my moles are going to cancel out, and I need to remember the gram molar mass, or calculate the gram molar mass for lithium nitrate. Lithium nitrate is 6.9 plus 14, so that's 20.9, plus 3 oxygens is 48, that's 68.9 is the gram molar mass. My moles cancel out. I do 68.9 times my 4.6, which was the number of moles that I have of lithium nitrate, and I get, I'll write it down here, 316.94 grams, which has far too many significant digits. We're really only allowed to have 2. That means I have 320 grams of lithium nitrate. Now that's what I got as an answer. Is that what I put in at the beginning? No, that's what I was asked to find though. So I was asked to find how many grams of lithium nitrate. I found that. I did that by going through the grams of lithium sulfate and used my balanced equation to make that happen. This is where all of stoichiometry comes together. Okay. Second page done. Now, these are the same sort of idea. There's only two problems now. This is what you will see on the test. There won't be the nice, friendly beginning parts. In order to make this happen, you've got to know what you're doing. So let me move this down a little bit more. You have a balanced equation. We'll assume that equation is balanced, although actually that one is not balanced. So in your test, I will not necessarily ask you to balance an equation, but if you did have to, you can see here, one potassium, that's good. One chlorine, that's good. 3 oxygens, 2 oxygens, we have a problem. Now, the best way I can figure is to have the lowest common multiple of these. If I had 3 O2s, and I had 2 KClO3s, and I had 2 KCl's. Now I have 2 potassiums, 2 chlorines, 2 chlorines, 6 oxygens, 6 oxygens. I have everything that I need. So the question is asking if 138.6 grams of potassium chlorate is heated and decomposes, what mass of oxygen is produced. So I write down what I know. 1,000, oh boy. My numbers are a little messed up. 138.6 grams of potassium chlorate. I have to now, with those grams, I have my balanced equation. I have to convert my units into moles. And I do that by dividing by the gram molar mass. So now for potassium is 39.1 we can call it, plus chlorine is really 35.5, and then I have 3 oxygens, which is 48. 16 times 3 is 48. My gram molar mass is 122.6. So my grams cancel out, all I'm left with are moles. So 138.6 divided by 122.6 equals 1.13 moles of potassium chlorate. Always write your units so that you can keep track of what you're working with. Okay, so from there, I have my moles of potassium chlorate. Now I can convert moles of potassium chlorate into moles of oxygen. What is it asking for? So I do 1.13 moles of potassium chlorate times, I want to cancel out potassium chlorate, so that goes on the bottom. My mole ratio is 2 to 2 to 3. So 2 moles potassium chlorate over 3 moles of oxygen. For every 3 moles of oxygen, I need 2 moles of potassium chlorate. For every 2 moles of potassium chlorate that are broken down, I make 3 moles of oxygen. I know that from my mole ratio. So when I feed this number through that conversion, it's going to get how much oxygen I produce, because I'm going to cancel out my units of potassium chlorate. That means 1.13 moles of potassium chlorate times 3 divided by 2 is 1.695. Now again, that's too many sig figs. I would say 1.70 moles of, look what's remaining. My potassium chlorate canceled out. I'm left with moles of oxygen. And then from there, I have to go my moles of oxygen into grams of oxygen. 1.70 moles of oxygen times 1 mole of oxygen goes on the bottom. The gram molar mass for oxygen goes on the top. Now remember, this is O2. Oxygen atoms are 16, but I have 2 of them. So now we're at 32 grams. My moles are going to cancel out. 1.7 times 32 equals 54.4 grams of oxygen. Is that what the question asked? What mass of oxygen gas is produced? Is that my number of grams of oxygen? Absolutely. If, and I'm not saying it did, but if this equation asked for liters of oxygen at STP, I would do 1.7 moles of oxygen, because we know oxygen is a gas, times 22.4 liters over 1 mole. And then my moles of oxygen cancel out, and I get 1.7 times 22.4, which is the liters of any gas at STP. That would be 38.08 liters, which of course is too many significant digits. It's basically 38 liters. If that asks for number of molecules of oxygen, again, I do my 1.7 moles of oxygen times 6.02 times 10 to the 23rd molecules over 1 mole, and I get 1.7 times 6.02 would give me 10.234 times 10 to the 23rd, which is wrong for scientific notation. It'd be 1.02 times 10 to the 24th molecules. But that's the different possible conversions we might have to make, because oxygen is a gas. I wanted to point them out. Of course, the one we need is 54.4 grams of oxygen. All right, I'm going to slide up, hoping it's balanced. Hopefully it's clear. I can move it up a little bit more. Okay, we can see everything. Dilute nitric acid. Copper metal dissolves according to the following equation. So we have this balanced equation. Is it balanced? We can double check if we really want. 3 coppers, 8 nitrates, 8 nitrogens. This is 2, that's times 3 is 6, and then 2 is 8 nitrogens. My nitrogens are balanced. 8 hydrogens, and then 8 times 3 is 24 oxygens. Here I have 2 times 3 is 6, 6 times 3 is 18, 18 plus 2 is 20, and then I have an extra 4, that's 24. So everything is balanced. And I'm out of focus. Okay. So now, how many grams of nitric acid are needed to dissolve 11.45 grams of copper? 11.45 grams of copper. I have my given. My given is that, grams of copper. Now I need to turn that into moles. First step, balanced equation. Second step, units to moles. In this case, grams to moles. So I have 1 mole over the gram molar mass for copper, which is 63.5. I can see it right there, 63.5. My grams are going to cancel out. 11.45 divided by 63.5 equals 0.18. Well, we really want to say 180 moles of copper. So that is my first thing. Balanced equation, my first conversion, units to moles. Now I find my mole ratio, which is 3 to 8 to 3 to 2 to 4. How many grams of nitric acid are needed, or hydrogen nitrate are needed to dissolve it? So, now I have the amount of copper I have. Now I need to feed that through my conversion. So for 3 moles of copper, I need 8 moles of nitric acid. That's my ratio. I pulled it from here. If I have 3 moles of copper, I need 8 moles of nitric acid. If I have 9 moles of copper, I need 24 moles of nitric acid. If I had 1 mole of copper, I'd have 8/3 for nitric acid. But in this case, I have 0.180 moles of copper times 8 divided by 3. I would need, for all of my copper to react, I would need 0.48 moles of nitric acid. Those are my only units left. Those canceled out. It's asking, however, for that value in grams. So 0.48 moles is now going to have to be turned back into grams. Hydrogen is 1, nitrogen is 14. That's 15. 15 plus 48 is 63. 63 grams is my gram molar mass. I got that from adding up the molar masses of the respective atoms on the periodic table. And then I have 1 mole. My moles cancel out. Every time I'm canceling out what I don't want. So 63 times 0.48 equals 30.24 grams of hydrogen nitrate. Is that what it was asking for? It absolutely was. The only thing is we have too many significant digits. We were working with 4. However, most of our stuff went down to 3. So I would just chop that off. 30.2 grams of hydrogen nitrate is a perfectly acceptable answer for that problem. Now we have one more side. And let's see how we get through this. This is one more challenging part because you're going to run out of something. This is a limiting reactant problem. I want to make sure I have everything lined up the way it needs to be. Okay, so when copper 2 chloride reacts with sodium nitrate, copper 2 nitrate and sodium chloride are formed. I first have to balance this equation. So right away I can see I have 2 chlorines here. I have 1 there. What if I double the amount of this? If I double the amount of this, now I have 2 sodiums. I have 2 sodiums now on both sides. 1 copper, 1 copper. 2 nitrates, 2 nitrates. 2 chlorides, 2 chlorides. 2 sodiums, 2 sodiums. Now I'm balanced. So that is my first step, balancing an equation. If 15 grams of copper 2 chloride react with 20 grams of sodium nitrate, how much sodium chloride can be formed? This is our limiting reactant problem. It's asking how much sodium chloride could be made. So I'm given grams, always, units to moles. That's your next step. 15 grams of copper 2 chloride, 20 grams of sodium nitrate. I'm going to turn them into moles. That's the only way any of this makes sense, is if I convert these things into moles. So copper 2 chloride, copper is 63.5, and I have 2 chlorides. 35.5 plus 35.5 is 71. Whoa, that's not the right number. 63.5 plus 71 is 134.5. So now that's my gram molar mass. Grams cancel out. I'm going to turn this into moles. 15 divided by 134.5 is 1. We'll call that 0.112 moles of copper 2 chloride. I'm going to do the same thing with sodium nitrate. I have 20 grams. Change that into moles. What's the gram molar mass here? It's 23 for sodium plus 14 is 37. My dog just made my paper a mess. All right, 37 plus Rocky. Oh, my dog is knocking onto the camera now. Okay. So 37 is my sodium plus my nitrogen, and then I have 48 for my oxygen, because 16 times 3 is 48. I have 85 grams for my gram molar mass of sodium nitrate. So 20 divided by 20 divided by 85 is 0.0112. I think we have something wrong here. I need to double check my numbers. 20 divided by 85 is not 0.0112. 20 divided by 85 is, yeah, okay. Something went weird there. So let's try that again. 20 divided by 85, 0.2352. So 0.235 moles of NaNO3. And let me just double check my numbers for the first part. 15 divided by 134.5 is, that one does work. So I have 1.112 moles of copper 2 chloride, and I have 0.235 moles of sodium nitrate. Now, it's asking how much sodium chloride can be formed. I have this many moles of copper 2 chloride. I have this many moles of sodium nitrate. One of these substances is going to run out. When one of them runs out, the reaction stops. I can't make any more sodium chloride if I run out of one of these. So what would I do? I look back at my original equation. How much sodium chloride would I make in this particular case? It would be 2 NaCl over 1 mole. We should keep the moles in here. 2 moles over 1 mole of copper. So I'm basically doubling the amount of sodium chloride. My moles here would cancel out. This ends up being, I would make 0.224 moles of sodium chloride. If all of my copper 2 chloride ran out, I would make 0.224 moles of sodium chloride. If I used up all of my sodium nitrate, here now the relationship 2, so 2 sodium chlorides, 2 sodium nitrates. My sodium nitrate moles cancel out. Again, I should have put a mole in there. I mean, for my purposes, I know what I'm doing. So 0.235 moles times 2 is then going to be divided by 2. I end up with 0.235 moles of sodium nitrate. If I use up all of my copper 2 chloride and the reaction stops, I have 0.224 moles. If I use up all of my sodium nitrate and the reaction stops, I make 0.235 moles of sodium chloride. So which one is going to run out first? It's going to be the smaller number. I used up all of my copper 2 chloride, the reaction stops. I will have some sodium nitrate left over. But my limiting reactant, because it produces less of my product, when it runs out, the reaction stops. My limiting reactant is going to be copper 2 chloride. Let me slide a little bit further so that maybe I can, can't quite keep everything on one page. One is the limiting reactant. You can only see it at the very, very top there. Try this again. Okay, what is the limiting reactant for the reaction in number 2? Because copper 2 chloride, when it runs out, it produces less sodium chloride. Copper 2 chloride is the limiting reactant. So we can only base all of our calculations on copper 2 chloride. How many grams of copper 2 nitrate are formed? It's the same idea as what we did with the sodium chloride. So I have 0.112 moles of copper 2 chloride, and my mole ratio, because I want to find copper 2 nitrate, so I have 1 mole of copper 2 nitrate over 1 mole of copper 2 chloride. My moles of copper 2 chloride cancel out. I make 0.112 moles of copper 2 nitrate. Now, that's a little bit messy. I have to go from moles to grams because that's my steps. Balanced equation. Now I do my mole conversion in this case to find out which runs out first. I use my mole ratio to find out what I don't know, which is copper 2 nitrate. I have that number of moles. Now I'm going to go from moles to grams. So 0.112 moles. Now our copper 2 chloride canceled out. Now we're dealing with copper 2 nitrate. I need to multiply that by the gram molar mass of copper 2 nitrate. So copper is 63.5. I have in this case 2 nitrogens, so that's 28. And I have in this case 6 oxygens, which is 96. 6 times 16 is 96. So my gram molar mass is 187.5 grams over 1 mole. That way my moles cancel out. 187.5 times 0.112 equals 21 grams of copper 2 nitrate. And then it says how much excess reagent is left over in this reaction. So, that is another, let me make sure I have enough space for it. How much excess reagent is left? So I need to find out how much did I use up. Which one did I decide was the limiting reactant? Was copper 2 chloride. How much sodium nitrate did I use up? I had 0.235 moles of sodium nitrate. Did I use all of that up? No, I have 2 moles over 1 mole of copper 2 chloride. I got that from my equation at the top. My moles of copper 2 chloride cancel out. I used up in this reaction 0.224 moles of NaNO3 sodium nitrate. But when I did my earlier calculation, if you look in letter B, which I can't show you on the screen right now, but if you look in letter B, which you should still have, you originally started with 0.235 moles of sodium nitrate. You used up 0.224. Once that 0.224 moles was used, the reaction stopped. So now I have 0.235 minus 0.224, which is 0.011 moles of NaNO3 remain. That's how much is left over. This doesn't specify, does it has to be in moles? If I wanted to do it in moles, now I multiply that by the gram molar mass, which for sodium nitrate was 85 grams. Could I do it? Sure. Do I need to? Not really. Just let's get to the very last part. If 11.3 grams of sodium chloride are formed in the reaction described in problem 6, what is the percent yield for this reaction? So in any of our calculations so far, did we calculate how much sodium chloride was made? If you look at B, we made, as a consequence of these calculations, we made 0.224 moles of sodium chloride. So this is what we call a theoretical yield. If everything worked perfectly based on having 15 grams of copper 2 chloride, which we calculated at the beginning, we know that's our limiting reactant. We know that's going to run out. In that perfect situation, we would make 0.224 moles of sodium chloride. If we change that into grams, gram molar mass for sodium chloride is 58.5. 23 for sodium, 35.5 for chloride, 58.5. My moles cancel out. I should, in a perfect situation, I should have made 13.1 grams of sodium chloride. I did not make that because not every atom in this equation actually found the other atoms. You never get perfect yield. That is what we did mathematically. That's how much we should have gotten. How much did we get? 11.3. This is a calculation called percent yield. So percent yield is your actual yield, what you actually measured, divided by the theoretical yield you calculated. You multiply that by 100, and that is your percent yield. So in this particular case, it is 11.3 over 13.1. This is what we actually measured. This is what we calculated we should have had. So 11.3 divided by 13.1 equals 0.8625. So if we keep this to 3 significant digits, we times that by 100, we end up getting 86.3% yield. That is our percent yield. You will have to do that on the test as well. But you just calculate your theoretical yield, and then you have your percent yield when you're done. With that, that concludes the entire worksheet, and that's a long video. Thank you.